Hello, my name is John Busel. I'm Vice President of the Composites Growth Initiative at the American Composites Manufacturers Association. The title of my presentation today is Advancements of FRP Composites in Transportation Infrastructure. So here's the outline of my opening remarks for this panel session. I'm going to cover a little bit about technology advancements, standards development activities, and our newly created FRP Composites education program. So ACMA has many active business industry councils in the Composites Growth Initiative program. The three that I have listed here are the most active in transportation infrastructure, and they include the FRP Rebar Manufacturers Council, the Transportation Structures Council, and the Pultrusion Industry Council. The member companies that are active in these three represent the composite supply chain. They work together to address industry needs. There have been many technology advancements over the years. I have a short list of products that are listed on this presentation here. Many products have been developed since the early 90s. Some of the products have been developed as industry collaboration. Some have been privately developed. All of the products listed have different stages of maturity, standards, and use. I'm going to focus on a few of these, which are the current innovations and those that are highlighted in yellow. So when we look at here, we have bridge decks, girders, rebar applications used in barriers and parapets, as well as in bridge decks themselves, pedestrian bridges, walkways, piling, bridge pier fendering, protection, seawalls, and concrete repair and strengthening. So one of the newest innovations that have taken place is the development of a new girder system called a composite tub beam, or G-beam, that requires no concrete fill. Over the years, there have been a number of girder systems that have been developed that utilizes FRP composites as well as concrete, and in some cases, high strength strands. This can be integrated with both a cast in place, a precast transverse, or longitudinal deck options. So it gives some variety for the owner of the systems. They can be designed at different depth and camber, and a lot of it depends on the project scope. Spans can include up to 120 feet, and others are also being looked at as far as longer spans. The inherent nature of composites that it's non-corrosive, low maintenance, and they're designed for a 100-year design life. Ideally, they are lighter than steel and concrete alternative systems. They are very supportive of the accelerated bridge construction type applications, excellent seismic performance, and they've been designed with the Ashtail LRFD designed specifications. So when you take a look at the comparison of this particular tub girder as compared to a precast Next 24 beam, there's a significant weight savings. And in some applications, if you're saving a lot of deck weight, that translates to the foundation and less reinforcement for the concrete abutments and piers. So there's a lot of benefit that would come from this. This picture here shows the installation of these composite tubs, and you'll notice on the picture on the left, two 75-foot girders being installed at once as an assembly. So again, notice the lightweight equipment that is utilized, and this really translates to faster installation time. So FRP pultruded truss bridges are not new. What is new is that the span lengths are getting longer. And here's a great example of a recent application that was installed last year. It's the world's longest FRP truss bridge. It was installed in Bermuda. It's 152 feet long with an 8-foot wide span. It was constructed in Pennsylvania, partially assembled in Pennsylvania, reassembled in Bermuda. But this is a unique application because of the span length. We've seen many of these type of truss bridges done a while back, but this gets into another category, and length is very important, especially as we're going over busy highways and other thoroughfares that are getting wider and wider. So FRP cantilevered sidewalks are becoming more acceptable as alternatives to rehabilitating both existing and constructing new shared pathways. It's a great alternative to historic bridges. Sidewalks are constructed of FRP sandwich construction, where the design loads, stress, sizes, and thickness can be customized to the application. There's much attention to safety and cost considerations, and especially when it's in a rehabilitation system, it oftentimes is the lower cost than a separate bridge or a separate pathway that would go along with that bridge. So it's something that continues to be a new trend as we're rehabilitating many of the bridges and having pedestrian walkways. So FRP bridge decks have been installed since 1996. And over the years, many types of bridges have been developed using multiple composite manufacturing processes. But here's a new innovation that has recently been tested by Missouri DOT. Again, it utilizes standard composite materials in a FRP deck configuration. It is not made by pultrusion. It's using a variation of a vacuum infusion process. It has been designed to AASHTO bridge requirements. It's being tested by Florida DOT, and preparations are for first installation at Florida DOT, but a recent bridge application has been installed in Tennessee. It was a short span bridge that was monitored and wired for that application. So it's again, the one thing that does happen with composites is that there's always new innovations. As I said before, bridge decks, either on existing or new construction, is not new. And it does provide a great alternative, especially in historic bridges. In this picture here, you'll see a historic bridge where the road surface was replaced with an FRP composite deck. You can see the panels that are being lifted with lightweight construction. It has integral curbs and scuppers and drainage, and it comes already pre-made with a road surface that is attached, and all are manufactured in the factory. And this will increase quality of the materials being produced and the product as an assembly, but also reduces installation time on the deck installation itself. We also have to include protecting our bridges. Here's a picture of a bridge fendering system that utilizes both pultruded pipe piles as well as whalers in the fendering application for protection of the piers. Again, lightweight construction, but not affected by the moisture in this particular application, and will always have a very good look for the duration of the life or service life of the bridge. in this application. You find this all up and down the East Coast, where you want to protect your assets. Rebar. It's been used in over 500 bridges in North America, has been applied in cast in place and precast concrete applications. We find them in long and short and notably cable-stayed bridges, interstate highways, or remote construction. Makes no difference. It is very much an accepted product where the rebar is high strength, lightweight, corrosion resistant. Here's this particular bridge in Minnesota, bridging the waterway to Canada. But there are many different applications, both in the countries of Canada and the United States. And certainly to that, we'll talk about this in the next section on standards development. There's been much testing, much analysis, and standards work and design guidelines that complement the use of the products in these applications. I show this, it is an installation being done in Florida DOT. It's a secant pile application. And what's unique about this is that it provides a barrier to assets along coastal waterways or ocean fronts. So we're seeing FRP rebar being used as the internal reinforcement for these concrete secant piles. So let me touch a little bit on standards development. Currently within the American Concrete Institute, there is a new dependent code that is being developed, which will certainly leapfrog the work that has been done with FRP rebar since the early 1990s. That is being written as a structure to the ACI 318 with 27 chapters, but 6 of which do not have anything to do with FRP. So just as an update, there's one final ballot that needs to be conducted at the main committee, and the next step is to go to the ACI Technical Activities Committee. It's unpredictable how long it will take. It's expected in late 2022 or even early 2023. But when published, this will change the marketplace because it will be the first time it's a FRP rebar code. Touched on by one of my colleagues, Mehdi Zargarmi, on the panel, the ASCE load and resistance factor design has gone through a very long process of taking this pre-standard and establishing this as a Structural Engineering Institute number 74, the LRFD design for pultruded FRP structures. So it's in its final approval, going to public ballot, and we hope to see this particular design guidance for pultruded structures being available to engineers for use very shortly. You know, I point this out, you know, there are many different design guidelines within AASHTO. Here's a list of those guidelines out there. I highlighted 2 of these guidelines that were recently published in 2018, which is the 2nd edition for the LRFD Bridge Design Guide Specifications for GFRP Reinforced Concrete, first of which was developed in 2009. This update in 2018 is written in an LRFD configuration for all concrete elements. Also, along with that, were guide specifications for pre-stressed FRP used in pre-stressed concrete. And I wanted to bring to your attention the number of standards that are available for in ASTM for rebar, and specifically wanted to point out D7957, which is the standard specification for FRP bars. A lot of science and a lot of knowledge has gone into this, but it's not necessarily limited to FRP rebar. There's also a number of standards that were developed for FRP concrete strengthening materials and systems. So there are certainly test methods that can be applied to our materials. And also wanted to point out certain DOTs, specifically Florida DOT, has integrated composites in both their materials manual and their design manual. I show the links here, and they're worthy of a reference and a look. And although not specific to transportation infrastructure, the International Code Council has developed two acceptance criteria, AC 454 and AC 521. One is for non-structural, one is for structural. What is interesting about these particular acceptance criteria are the recommended materials for reference. So it's a good reference standard for users and engineers. So I just want to touch a little bit about education that the composites industry has been undertaking in recent times. We have conducted a Composites Technology Day. It was an event to educate designers, specifiers, engineers, contractors on the benefits of FRP composites to solve infrastructure problems. We conducted it last month. The days were themed, 4 different days, 21 presentations in all, and it was brought to you by the American Composites Manufacturers Association. The link is located here. This is just a snapshot of the overview of the program. As you can see, we cover a lot of different aspects with vehicular decks, beams, girders, pedestrian bridges, corrosion applications in industrial structures, fender piling, seawalls, concrete strengthening, architectural applications, heavy civil structural, as even touching on life cycle cost analysis and how we need to approach composites. If you're interested for more of this, we can talk about this later so you can have access to this information. And with that, I close my opening remarks. Here are my credentials as far as contact information, phone, and email, and look forward to taking any questions that you may have during this panel session. Thank you very much.